In the previous lesson, we spent some time talking about solving linear equations. My goal in this lesson is to take that a step further and to look at solving a very special set of equations which involve absolute values. Before we can start solving these equations, we need to spend a few minutes talking about what absolute values really are. And to do that, we have to go back to the idea of the real number line. Remember that the real number line is a way to see or to visualize the set of real numbers. It's usually drawn as a horizontal line with tick marks or vertical lines marking the locations of several numbers on the line. We often label the real number line with the 0 in the middle. And this point is very special to us. It sort of gives us a good way to start, and we give it a particular name. We call that place the origin on the number line. We can then label as many other points as we want on the line, and usually we pick a few whole numbers to label, maybe from -4 up to 4. Once that's done, we can now talk about the idea of the absolute value of a number. The absolute value of a number is most often written with two vertical lines, one on either side of the number. So, for example, the absolute value of 4 is written as a 4 with a vertical line on each side, while the absolute value of the number -5 is written as -5 with a vertical line on each side. But what does this symbol mean with these vertical lines? Well, to be honest, it doesn't mean anything more than the distance from the origin on the number line to that particular number. So, for example, absolute value of 4 means the number of steps we would have to go from the origin, or the 0, to the number 4. Well, that would be 4 steps. You'd have to start at the 0 and then just go 1, 2, 3, 4. So, absolute value of 4 is just 4. Well, how about the absolute value of -3? Well, how far is the number -3 from the origin on the number line? The answer is 3, because if we started at the origin, we'd have to go one step to the -1, then another step to the -2, and then a third step from -2 to -3. And that means that the absolute value of -3 is exactly 3. And I want you to notice that it's +3, not -3. So, what do we see from those two examples that I just mentioned to you? Well, first, the absolute value of any number is really just a distance more than anything else. And I think that's an extremely important way to remember absolute values. And the second important thing is that the absolute value of a number is always positive. Well, it's not always positive, because the absolute value of 0 is just 0, and 0 is not usually thought of as a positive number. But the absolute value of every number other than 0 is always positive. So this is very important to remember. And thirdly, there's a way to write the absolute value in a sort of algebraic way so that you really don't need the vertical lines. That is, if x is greater than 0, then absolute value of x is just equal to x. While if x is less than 0, then the absolute value of x is equal to the negative of x. So, for example, when we did absolute value of -3 before, we saw that it was equal to 3. Well, another way to get that 3 would have been to take the negative of -3. And the negative of -3 is exactly equal to 3. So I can actually write absolute values without those lines if I really want, keeping these algebra rules in mind. Bottom line, if someone comes to you and says they've found an absolute value and it's equal to something like -2 or -7, you automatically know it's wrong. This is part of the critical thinking we need to do about absolute values. So let's move to a slightly more complicated example where I want to do an absolute value, but I need to do an absolute value of something that looks a little more complicated than just one number. Let's find the absolute value of 3 times the quantity 4 minus 15 plus 10. From what I know about order of operations, I know that I need to simplify what's inside the parentheses first before we can do anything else. So the first thing I'm going to do is compute 4 minus 15, and that gives me negative 11. And so the original problem is now whittled down to the absolute value of 3 times negative 11 plus 10. I then need to do the multiplication next, and that's going to give me absolute value of negative 33 plus 10. And that, of course, is the same as absolute value of negative 23. Negative 33 plus 10 is negative 23. So now I know that I just want how far negative 23 is from the origin. That's what absolute value of negative 23 means. And the answer there is 23. So I know that the original number that I wanted, which was pretty complicated, absolute value of 3 times 4 minus 15 plus 10, is exactly equal to 23. Okay, let's move to another example of this type. Here now I want to start with an absolute value which has some variables in it, but I want to plug in a particular number for the variable and see what I get. Let's find the absolute value of negative 4x times x minus 3 squared when x is equal to negative 2. So the first thing I'm going to do is substitute the value negative 2 in for x throughout the expression. And when I do that, I'm going to have absolute value of negative 4 times negative 2 times the quantity negative 2 minus 3 squared. Now I've got to walk through my order of operations. The first thing I need to do is to simplify what's inside those parentheses. So that means I'm going to have absolute value of negative 4 times negative 2 times negative 5 squared. And after I've computed what's inside those parentheses, I now need to do the exponentiation. And that means I need to compute negative 5 squared. Well, negative 5 squared is negative 5 times negative 5, and that's equal to positive 25. So now what I'm down to is the absolute value of negative 4 times negative 2 times 25. I now perform those multiplications, and of course, negative 4 times negative 2, let's see, that's positive 8. Remember, when you multiply two negative numbers, you get a positive back. So I'm really down to absolute value of 8 times 25, which is the absolute value of 200. And this is 200 because the number 200 is exactly 200 units away from the origin. So my final answer is 200. Okay, with those examples done, I want to move to some more examples of solving equations, this time where the equations have absolute values in them. Now these are going to be slightly different from just solving linear equations. They kind of look linear, especially if you don't look for those vertical lines, but once you've thrown those vertical lines in and you have absolute values, the problems get slightly different and a bit more difficult. They're not impossibly difficult, but they are different. So let's be careful as we walk through these examples. The first one I want to look at is this. Solve the equation absolute value of 2x minus 4 equals 14. Now, let's say something very, very important about this kind of equation that is true for all of these kinds of equations. There are lots of students who believe that the way to do this kind of a problem is just to erase the absolute value symbols and just to solve the equation 2x minus 4 equals 14. It turns out that this isn't really a bad idea, but it's not the whole idea. It's only half of the solution of the problem. What you really have to do to solve the problem correctly and completely is to actually convert the original equation into two separate equations. And you have to solve 2x minus 4 equals 14, and you have to solve 2x minus 4 equals negative 14. Why? Why do you have to do that second equation, 2x minus 4 equals negative 14? Well, it's because when we say absolute value of 2x minus 4 is 14, we're saying that the quantity 2x minus 4 lives either 14 steps to the left of the origin or 14 steps to the right of the origin on the number line. So actually solving the equation absolute value of 2x minus 4 equals 14 is really solving two different problems. Now, if you think you've got the idea, why don't you stop the video at this time and see if you can solve those two equations from here. Well, do you think you got the right answers? Let's look at them ourselves now. Let's attack the two problems separately and see what you get. We start by solving 2x minus 4 equals 14. If I add 4 to both sides of that equation, I'm going to have 2x equals 18. And now if I want to get that x by itself, I just divide by 2, and I will have x on the left equals 9. So it looks like x equals 9 is a solution. Let's check by plugging 9 back in for x in the original equation. That's going to look like absolute value of 2 times 9 minus 4, which is the same as absolute value of 18 minus 4, which equals absolute value of 14, which is 14. And that was the right-hand side of what we started with. So that's fabulous. But we're not done. We've only done half the problem. The original equation could also be 2x minus 4 equals negative 14. Now let's solve that equation and see what we get. Well, 2x minus 4 equals negative 14 is the same as 2x equals negative 10. How do I get negative 10? I add 4 to both sides of the equation. And from 2x equals negative 10, I can convert to x equals negative 5 by dividing both sides by 2. So it also looks like I have a second solution, x equals negative 5. Let's check that by plugging negative 5 into the original equation. When I do that, I have absolute value of 2 times negative 5 minus 4, which is absolute value of negative 10 minus 4, which is absolute value of negative 14, and the absolute value of negative 14 is 14. And that was the right-hand side of the original equation, so negative 5 really is a solution as well. And it turns out that our original equation then has two solutions, not just one. X equals 9 and x equals negative 5 are both solutions. And that's fabulous. It turns out that finishes that example. Both of those numbers really are solutions. Now, before I go to another example, I need to emphasize one point quite a bit, and here it is. It's extremely important in these kinds of problems that we check all of our solutions to make sure that they really are solutions. Believe it or not, there are lots of ways that sort of false or phony solutions can pop up in these problems. Not because we've done anything wrong, but because of the way the problems are done. You can actually have some false solutions. The only way to know whether we have all of the correct solutions is to plug those numbers back into the original equation to make sure they really work. So although it takes some time and sometimes it's a bit tedious, let's make sure we plug those answers back in to confirm that they really are solutions before we move on to the next problem. So with that in mind, I want you to try solving one on your own and check both answers to see if they work. Here's an example I want you to work on. Solve the following equation. 4 times the absolute value of 3x plus 1 minus 7 equals 13. Now, did they both work? Well, I'll tell you, let's try solving it together and let's make sure that I get the same solutions that you did. So this equation actually requires a little bit of rewriting before we really find the solutions. And that rewriting basically means that I want to get the absolute value symbol by itself. So let's start with the original equation and do some things, some algebra that's legal to do to get the absolute value by itself. We started with 4 times absolute value of 3x plus 1 minus 7 equals 13. Let's add 7 to both sides to give me 4 times absolute value of 3x plus 1 equals 20. And now I can divide that 4 from both sides of the equation. And when I do that, on the left-hand side, it'll go away. I'll have absolute value of 3x plus 1. And on the right-hand side, I'll have 20 divided by 4, which is 5. So I'm now down to an equation, absolute value of 3x plus 1 equals 5. Now, from the example that I just did a few moments ago, we know that this is really two different linear equations. Either 3x plus 1 equals 5 or 3x plus 1 equals negative 5. So now I need to solve each of these one at a time and check the answers to make sure that they really are solutions of the original equation. So the first equation was 3x plus 1 equals 5. If I subtract 1 from both sides, I'll have 3x equals 4. And dividing both sides by 3, I have x equals 4/3. Did you notice how we just solved a two-step equation just like we did a few lessons ago? It's great. This stuff is building on itself. We're mastering those basics. So one possible solution is x equals 4/3. Now remember, the other equation was 3x plus 1 equals negative 5. Subtracting 1 from both sides gives me 3x equals negative 6. Dividing by 3 gives me x equals negative 2. So I have two possible solutions. X equals 4/3 and x equals negative 2. Let's check that each of these is a solution by plugging them back into the starting equation. The original equation was 4 times absolute value of 3x plus 1 minus 7 equals 13. If I plug in 4/3, I have 4 times absolute value of 3 times 4/3 plus 1 minus 7 equals 13. And the material inside the absolute value simply becomes 4 plus 1. 3 times 4/3 is just 4. So what I really have is 4 times absolute value of 5 minus 7 equals 13. Absolute value of 5 is just 5, so I have 4 times 5 minus 7 equals 13. 20 minus 7 equals 13, or 13 equals 13. And since 13 equals 13, I know that what I plugged in the beginning, x equals 4/3, really is a solution. Now, let's try plugging in the other value, x equals negative 2. Well, if I do that, I'll have 4 times absolute value of 3 times negative 2 plus 1 minus 7 equals 13. 3 times negative 2 is negative 6. Negative 6 plus 1 is negative 5. And so what I now have is 4 times absolute value of negative 5 minus 7 equals 13. Remember, absolute value of negative 5 is positive 5. So now I have 4 times 5 minus 7 equals 13. That's 20 minus 7 equals 13, which is 13 equals 13. And that works. So x equals negative 2 is also really a solution. Now I have to ask you, is that what you found also? I hope it is. Both of those numbers really are solutions. Now, let's move to some other equations that come up in this kind of work, again, where you have absolute values floating around in an equation. Let's solve the following example. Absolute value of 7x minus 19 equals negative 10. Now, we need to be a bit careful and think about this equation for just a second. Let's do some of that critical thinking together. Notice that the left-hand side of this equation is just one big absolute value. And we know that no matter what's inside the absolute value symbols, the absolute value either is 0 or a positive number. But look at the right-hand side of the equation. It's a negative number, negative 10. So the left-hand side is either 0 or something positive, while the right-hand side is negative. What do we conclude? What's the answer then? We know then that the original equation has no solutions because there are no numbers which are both positive and negative at the same time. So that equation actually had no solutions, and that's a possibility. We've already seen examples of equations in a previous lesson where we had no solutions. The same sort of thing can happen with these absolute values. Now, let's look at another example where the variable x shows up in more than one place. This can easily happen. So let's try the following. Solve absolute value of 6x minus 2 equals 5x plus 3. Now, let's go back to one of the main ideas in this lesson, that this kind of equation has to be broken into two separate equations. The first one is just 6x minus 2 equals 5x plus 3. That's the one you get when you basically erase those absolute value symbols. But remember, you're not erasing them. You're simply thinking of that piece as positive. But the other equation that can come up with is 6x minus 2 equals the negative of the right-hand side. So we would have 6x minus 2 equals the negative of 5x plus 3. Notice that the negative sign on that right-hand side of the second equation has to impact both the 5x and the 3. In other words, I don't want to write down negative 5x plus 3 for the right-hand side, because that's very different from negative quantity 5x plus 3, which actually equals negative 5x minus 3. So I now have my two equations. Let's solve each of those two equations separately and see what we get. The first equation was 6x minus 2 equals 5x plus 3. If we move the 5x over to the left, or just subtract 5x from both sides, we will have x minus 2 equals 3. And now adding 2 to both sides of that equation gives me x equals 5. So one of the possible solutions is x equals 5. Now if I go to the second equation I had written down, which was 6x minus 2 equals the negative of 5x plus 3, I'm looking at 6x minus 2 equals negative 5x minus 3. Adding 5x to both sides gives me 11x minus 2 equals negative 3. Adding 2 to both sides of that gives me 11x equals negative 1. And if I just divide by 11, I have x equals negative 1 over 11. And that gives me a second possible solution. So I have x equals 5 and x equals negative 1 over 11 as potential solutions. The only way we can confirm or guarantee that they really are solutions is to plug them back into the original equation and see if they work. So let's do that now. Let's start with the first of the possible solutions, x equals 5, and plug it in. I'll have absolute value of 6 times 5 minus 2 equals 5 times 5 plus 3. On the left-hand side, I'm going to have absolute value of 30 minus 2, which of course is absolute value of 28, which is just 28. On the right-hand side, I have 5 times 5 plus 3, which is 25 plus 3, which is 28. And that means that the left-hand side and the right-hand side are both 28. And that's true, and therefore, x equals 5 really is a solution of the original equation. That's good to go. Now let's try the other potential solution, negative 1 over 11. Well, the arithmetic's going to get a bit messy, but it's okay. We can work our way through it. Here I'm going to have absolute value of 6 times negative 1 over 11 minus 2 equals 5 times negative 1 over 11 plus 3. The left-hand side becomes absolute value of negative 6 over 11 minus 2. Getting a common denominator gives me absolute value of negative 6 over 11 minus 22 over 11. And now if I look at my right-hand side for just a second, I've got negative 5 over 11 plus 3. Again, getting a common denominator is going to give me negative 5 over 11 plus 33 over 11. Now, if I simplify both sides of that equation for just a moment, the left-hand side becomes absolute value of negative 28 over 11, and the right-hand side becomes 28 over 11, and both of those sides are just equal to 28 over 11. That means that x equals negative 1 over 11 is also a solution. So both of those numbers really were solutions. Now I'd like you to see if you can solve one of these on your own, and let me give it to you here. Solve absolute value of 3x plus 5 equals 5x plus 2. Now let's do it together, and let's see if the numbers you got were correct. Again, I'm going to split this into two equations, and I'm going to solve each one separately. And those two equations are going to be 3x plus 5 equals 5x plus 2, or 3x plus 5 equals the negative of 5x plus 2. Let's do these separately now. 3x plus 5 equals 5x plus 2. If I subtract 3x from both sides, I get 5 equals 2x plus 2. Subtracting 2 from both sides now gives me 3 equals 2x. Now you might be saying, wait a minute, your x is on the right-hand side. Remember in a previous lesson I talked about how the x's could be on one side, the numbers could be on the other. It doesn't matter which is which. So 3 equals 2x, no problem. Now divide by 2 on both sides, and you'll basically have x equals 3 halves. That's one possible solution. Now let's look at the other equation. 3x plus 5 equals the negative of 5x plus 2. That's the same as 3x plus 5 equals negative 5x minus 2. Make sure that that negative sign gets distributed all the way through the parentheses. And now if I add 5x to both sides, I'll have 8x plus 5 equals negative 2. And if I subtract 5 from both sides, I'll have 8x equals negative 7. Dividing by 8 gives me x equals negative 7/8. So now I have two numbers that are potential solutions. I've got to plug them in to see if they really are solutions. So I plug them back into the original equation. The first one is absolute value of 3 times 3 halves plus 5 equals 5 times 3 halves plus 2. Well, what's that going to give me? Well, the left-hand side is absolute value of 9 halves plus 5, and that equals 15 halves plus 2. And now I need to get a common denominator, which is not a problem. That's just going to be a 2 all the way through. And the left-hand side becomes absolute value of 9 halves plus 10 halves, and that equals the right-hand side, which is 15 halves plus 4 halves. Now let's do some simplifying. The left-hand side is the absolute value of 19 divided by 2, and the right-hand side is just 19 divided by 2. And both of those sides are just equal to 19 divided by 2, or 19 halves. And that means x equals 3 halves really is a solution of the original equation. And now let's try that other number. Let's see if it was also a solution. Well, if I plug in negative 7/8 into the original equation, I have absolute value of 3 times negative 7/8 plus 5 equals, on the right-hand side, 5 times negative 7/8 plus 2. And now let's do some simplifying. The absolute value on the left is going to be absolute value of negative 21 over 8 plus 5. Right-hand side becomes negative 35 over 8 plus 2. Let's get that common denominator. Now in this case it'll be 8s all the way across. And when you do that, you'll have absolute value of negative 21 over 8 plus 40 over 8 equals negative 35 over 8 plus 16 over 8. Now let's simplify. The left-hand side is absolute value of 19 over 8. The right-hand side is negative 19 over 8. But since absolute value of 19 over 8 is 19 over 8, I now have the equation 19 over 8 equals negative 19 over 8. We've done everything correctly. So what do we conclude? We conclude that the number I just plugged in, negative 7/8, is not a solution of the original problem. I like to think of these as false solutions, if you will. But false solutions are not solutions. You don't want to keep x equals negative 7/8. So what this means is that we really only had one real solution. And we're going to call this x equals negative 7/8, which is a phony solution, a special name. We're going to call it an extraneous solution. An extraneous solution is a solution of an equation which came from an original equation, but is not the solution of the original. So we don't want to keep this x equals negative 7/8. It's not a real solution of the original equation. And that means that there's really only one solution to keep, and that's x equals 3 halves. Now you can see why I kept saying, we've got to check answers, we've got to check answers. Sometimes, even when we've done everything correctly, these false solutions or extraneous solutions try to sneak in. We have to watch for them, and we have to throw them out. Now, to finish this lesson today, I want to solve one more equation of this type. So let's do this one. Solve absolute value of x minus x equals 2. Well, let's do the first thing first. Let's get that absolute value term by itself. Add the x to the right-hand side, and you'll have absolute x, or absolute value of x, equals x plus 2. So we're trying to solve two equations. X equals x plus 2, and x equals the negative of x plus 2. That's always what you need to do with absolute value equations. The first equation, x equals x plus 2, gives you just 0 equals 2 when you subtract x from both sides. Okay, 0 is not equal to 2. So that equation is not going to give you a solution at all. The other equation that we had gives us something better. X equals the negative of the quantity x plus 2 is the same as x equals negative x minus 2, which is 2x equals negative 2, or x equals negative 1. Let's quickly check that x equals negative 1 is a solution. Let's see. I'll have absolute value of negative 1 minus negative 1 equals 2. That's the same as 1 minus negative 1 equals 2, since absolute value of negative 1 is 1. And that's the same as 1 plus 1 equals 2, or 2 equals 2. And since that checks, we know that x equals negative 1 is our one and only one solution of the original equation. Well, in this lesson, we've talked about absolute values and how to solve equations that involve them. Next time, I want to talk about linear equations and functions and look at the graphs of these things, and also look at parallel and perpendicular lines. I look forward to talking with you then.